Various geometric transformations in the plane or in three-dimensional space, like scaling, rotation, shearing, orthogonal projection, and reflection, can all be accomplished through matrix multiplication. In this video, let's explore two-dimensional transformations. When we write a matrix multiplication like matrix A times vector x equals vector y, the matrix A here is a 2 by 2 matrix. The input vector x is a 2 by 1 column vector, which we can think of as a point in the two-dimensional Cartesian plane. The output y is also a 2 times 1 column vector, representing another point in the same plane. If the matrix A is a diagonal matrix, then matrix A times vector x equals y amounts to performing a scaling transformation in the plane. When the main diagonal entries are equal, we have a uniform scaling. If the main diagonal entries are different, we have a non-uniform scaling, meaning the scaling factors differ in the horizontal and vertical directions. And the determinant of the square matrix A tells us the factor by which areas are scaled under this transformation. Now let's take a look at this matrix on the screen. It rotates shapes around the origin by an angle theta in counterclockwise direction. Clearly, rotation does not change the area of a shape or the order of basis vectors. So the determinant of rotation matrix is 1. In the plane, a horizontal shear slants the shape sideways while keeping the vertical coordinates unchanged. As you can see, when k is greater than 0, the shape leans to the right. When k is less than 0, it leans to the left. The larger the absolute value of k, the stronger the shear, the more pronounced the slant. The vertical shear, on the other hand, slants the shape upward or downward, while keeping the horizontal coordinates fixed. Please explore on your own exactly how different values of k affect the geometry of the shape in vertical shear. On the screen, we have the non-zero vector tau starting at the origin. An orthogonal projection sends points onto the line through the origin in the direction of vector tau. As the angle vector tau changes, the resulting orthogonal projection of the shape changes accordingly. Please note that orthogonal projection always loses some information. Geometrically, it collapses the area of a 2D shape down to 0. That is why the determinant of projection matrix is 0. In the plane, a reflection maps a geometric shape to its mirror image across some line through the origin. As the angle of this mirror line changes, the position of the reflected shape changes too. Even though reflection preserves area, it does flip the shape, so the order of basis vectors is swapped. That is why the determinant of reflection matrix is -1. Translation in a plane can also be done with a matrix multiplication, but we upgrade from a 2 by 2 matrix to a 3 by 3 matrix. On the screen, in this 3 by 3 matrix, T1 represents how far the shape moves horizontally, and T2 shows how far the shape moves vertically. Adjusting T1 and T2 shifts the shape accordingly.